All right, this is Unit 4, Lesson 5. Unit 4 is called Applications of Differentiation. Lesson 5 is called Related Rates with Circles and Spheres. This is part 2 of Lesson 4. We talked about related rates with rectangles and triangles. So again, more examples of using derivatives with related rates in a context. Did you know that how do you say this? The perimeter of a circle or the circumference is the derivative of the area of a circle. Think about it. Area of a circle, pi r squared. Perimeter of a circle or the circumference, 2 pi r. That's just a power rule. Yeah? Mind blown? So using calculus language, if the area of a circle is pi r squared, then the derivative of the area of a circle with respect to the radius is 2 pi r. Interesting. What about a sphere? Well, the volume of a sphere, this is not a smiley face, this is my attempt at drawing a sphere. The volume of a sphere is 4/3 pi r cubed. Derive that, you get the surface area of a sphere, 4 pi r squared. 3 times 4/3 is 4. Subtract 1 from the exponent. Yeah? Mind blown? Sadly, if you try this calculation with some other of our perfect polyhedra like cubes, it doesn't quite pan out as smoothly. For example, the volume of a cube is surface area cubed, but the derivative of the derivative of the volume of a cube is actually like double the surface area of the cube. So it doesn't quite work out on that one. But for circles, it is beautiful. So, example here, rate of change. We have a circle, and the area of the circle is increasing at a constant rate of 100 square centimeters per second. At the instant when the radius of the circle is 4 centimeters, what is the rate of change of the radius? Or how much is the radius growing by or shrinking by at that instant when the radius is 4 centimeters? So it's an area question. We'll start with the formula for the area of a circle. Area is pi r squared. The derivative, so again, since we're taking with respect to time now, because we're trying to find at what point in time is the radius, words. Yeah, we're trying to find the derivative with respect to time because this thing is changing per second. And so we do the r variable implicitly with respect to time. So we do have to do this implicitly differentiation. So the derivative of the area is 2 pi r times dr dt. And so that's the derivative equation. So now we plug in the information we have. We want to find the rate of change of the radius. That's dr dt. That's what we're solving for. At the instant when the radius of the circle is 4 centimeters, well, that's r is 4. The area of a circle is increasing at a constant rate of 100 square centimeters per second. So the change in area over time is 100. So dA dt 100, r 4. The remaining variable is dr dt. So if we solve this thing for dr dt, we just basically divide 100 by 2 times 4 times pi. We get 100 over 8 pi, which is 25 over 2 pi, and it's in centimeters per second. So this is a little different from the last one. The last lesson, we're given always the information on the right. This time we're given the answer and one of the pieces of information, and we have to find the missing piece of information. That's fun. This example will be analogous to that, except we're talking about a sphere. So the volume of a sphere, this should say sphere, I missed one of the two typos, is decreasing at a constant rate of 60 cubic feet per second. So the ball is shrinking. Probably a balloon full of air and it's losing air. At the instant when the radius of the sphere is 10 feet, what is the rate of change of the radius? So the area of volume of a sphere, this should be V, we'll just call it A. It's 4/3 pi r cubed. So the derivative of the volume with respect to time would be 4 pi r squared And since we're taking it with respect to t, we implicitly derive r, so we multiply it by d r dt. And then we want to find what is the rate of change when the radius is 10 feet. So we want to find d r dt. We're given r at that point is 10. Our constant decreasing rate of 60 cubic feet per second means we have negative 60 as our d, the change in volume over time. So then we just solve this for d r dt. We get um, a negative rate of change, which makes sense. If the volume is decreasing, the radius should be getting smaller. So this should be negative. If you got a positive here, in this context, you did something wrong. Okay, here's our flex for today. Rate of change of the cone. So the cone, the radius of the cone is increasing at a constant rate of 2 meters per second. And the volume is increasing at a rate of 333 cubic meters per second. So as water goes up, the radius of the surface is getting wider, which means the volume is going up, basically, yeah. But the higher we go up, the slower the water level is going to raise because the radius is getting wider. It means it takes more water to get every incremental inch. So a steady amount of water added to this cone is going to increase the height, which therefore increases the radius at a decreasing rate. And this one's just nasty because although it's the exact same concept as before, the more complicated stuff gets put into our equations. So at the instant when the radius of the cone is 8 meters and the volume is 170 cubic meters, what is the rate of change of the height? Well, the height is a function of the radius, right? So we do have to say, okay, the derivative of the volume of a cone, well, volume of a cone is right here. So the derivative of the rate of change of the volume of a cone, dv dt, would be 2/3 pi r. And then this is variable r, variable h, so that is a product rule. So it's r dr dt times h plus the whole first chunk times the derivative of h with respect to t. So first times derivative of second plus second times derivative of the first, or in this case, I did that backwards. Once we do that, we have our derivative equation, or our change in volume with respect to time. Just plug in all the information we know. The change in volume, the rate is 333 cubic meters per second, so that's dv dt. Our radius is when the cone has a radius of 8 meters, so 8 there, 8 squared here. Our, ooh, yeah, here's what's nasty. Our height. Our height is when our radius is 8, we can calculate the height of this thing. So the, how do I say that? The rate of change of the radius over time, when the cone is 8, has a radius of 8 meters, its volume is 170 cubic meters. So we kind of use that volume and that radius and plug it in to the volume of a cone equation. That's all this is right here. And then we want to solve for h, because nowhere in our information are we given the height at this point in time. So because it has pi in there, when we solve for h, we just get this nasty 3 times 170 over 64 pi. Gross. Don't like it, but whatever. We'll tuck that, plug it in for h right there. That's our height. Gosh, it's nasty. Okay, dr dt is the change in the radius in time. So the radius of the cone is said to be increasing at a constant rate, which means the water flowing here is probably not at a constant rate. That's tricky. I don't like that. Since the radius of a cone is increasing at a constant rate of 2 meters per second, 2, positive 2 is our dr dt. Right there. Dr dt is 2. Okay, radius, also 8. The change in height over time is what we're trying to calculate. So basically, we're going to take this whole thing right here, this whole term and subtract it from 333. And then all this business right here is being multiplied by a DHCT. So we'll take that and slap it in the denominator. And then we're not going to simplify it because 1 is nasty, 2 we don't care because it's calculus. Calculus, we care about doing calculus, which we have done. We'll leave the calculations for the calculator. Okay, so we can use calculus to model related rates of change in context. And again, more confidence working with derivative, understanding derivative, and that's all great stuff.